Hello everyone, welcome to Calc Lesson number 40. This is our second day of optimization. Today we're going to be looking at the volume and surface area of a box and then also the area and perimeter of a rectangle. Okay, let's jump right in with our first example. It says a supermarket employee wants to construct an open top box, so a box with no top, from a 14-inch by 30-inch piece of cardboard. So the first thing we want to recognize is that we have a flat piece of cardboard. So a rectangle, it is 14 inches by 30 inches. And in order to do this, the employee plans to actually cut squares out of each corner so that he can fold the four sides up. So if that's not really quite making sense to you, maybe you want to go ahead and pause the video, grab a piece of paper, and think about how folding that up would create an open top box. So we need to decide what size should the squares be so that we have a box with the largest possible volume. So we need to come up with a way to measure the squares, and then we need to create a volume equation. Because these are going to be squares, the length and the width of each of them is going to be the same, but we don't know what it is. So let's go ahead and label these squares as x by x squares. When we do that and we fold up to create our box, that makes this new side of our box 30 inches minus 2x, and this new side of our box 14 inches minus 2x. So when we fold everything up, our box will be 30 minus 2x by 14 minus 2x. Thinking about that, since we're creating a real-world equation, let's just consider our domain for a second. Because we are actually cutting off corners, there is a restriction there. Because of this 14 minus 2x, the largest amount we'd be able to cut off would be 7 inches, and even then that would be a little bit too much because we would be left with absolutely nothing. And then obviously the smallest amount we could cut off would be nothing if we didn't cut anything off. So our domain here in this real world situation would be from 0 to 7 since we are cutting off those corners. So now what we want to do is create our volume equation, and hopefully you remember that volume of a box would be equal to length times width times height. In this case, our length is going to be equal to 30 minus 2x. Our width would be 14 minus 2x. And if we fold up with our x by x square as the cutout, our height is actually going to be x. And again, if you're unsure of how that works, feel free to pause me, grab a piece of paper, cut out some squares, and measure that height and prove to yourself that yes, it would be the part that you cut off. Once we've done this, we've created our equation, we want to maximize volume. So just like we did yesterday, we're going to be using that first derivative. However, we know that it is much easier to take a derivative from an equation in standard form than in factored form. So we're going to go ahead and actually multiply this out. So we have our volume equals, I'm going to put my x to the front for now. Foiling out, 30 times 14 gives me 420 minus 60x minus 28x plus 4x squared, and then all in one step here, I'm going to rewrite this in standard form, combine like terms, and distribute that x through. So I have volume equals 4x cubed minus 60x minus 28x gives me a minus 88x, and I'm going to distribute this x to get x squared plus 420x. So this is my volume equation that I want to maximize. So in order to maximize it, I'm going to go ahead and take the derivative. So v prime equals, using my power rule, 12x squared minus 88 times 2 would be 176, x to the 1 less power, which is 1, plus 420. This is where the real fun starts. We want to set this equal to 0 and solve. I'm going to do an extra step here and actually take out my greatest common factor, which I'm recognizing as 4. So if I pull a 4 out, I'm left with 3x squared minus 44x plus 105, and this is going to be equal to 0. I get to solve this quadratic using really any method that I want. I could try to factor, or I could use the quadratic formula. I'm going to factor this using the AC method just as a quick review, but if you wanted to jump to the quadratic formula, please feel free. So I have 4 times, let's do 3 times 105, gives me 315. I'm looking for factors of 315 that add up to negative 44. 315, let's see, adds up to 9. Let's try dividing by 9, gives us 35. 9 and 35 is going to work, so let's do minus 9x minus 35x plus 105 equals 0. AC method, so I have 4 on the outside, taking out my 3x. I get, whoopsie, x minus 3, taking out my 105, actually divides by 35, which is good. Taking out a negative 35, we're left with x minus 3 equals 0. Let's come up to the top here. So we have this 4 on the outside, and then we can factor this to be 3x minus 35 and x minus 3 equals 0. Zero product properties, as we can set each of these factors equal to 0. So we have 3x minus 35 equals 0 and x minus 3 equals 0. So we get x equals 35 over 3, which is about 11.7, or x equals 3. This is why it was important to identify our domain earlier, because 11.7 is actually not in our domain. We cannot cut that much off of each side. So we're going to go with x equals 3. So the question says, what size should the squares be? So our squares should be, and we are measuring here in inches, so 3 inches by 3 inches in order to maximize the volume of our open box, of our open top box. Okay, number 2 is going to be similar, but a little bit different. So number 2 says a manufacturer wants to design another open top box, this time having a square base, and then we have information about our surface area of 108 square inches. But then we're asked to find the dimensions that will produce a box with maximum volume. So kind of a lot happening here. We have maximum volume and surface areas mentioned. So in order to solve this, I'm going to need to sketch a picture. And admittedly, I am a horrible box drawer, so bear with me. We want to draw a box that has a square base. So I need a square for sure. And I know it's a square, so it's x by x. And then it has an open top, so it doesn't say how tall it is, so I'm just going to estimate here. It's something like this. And we don't know the height, so I'm going to write it as h because I'm unsure, but it's not the same as x, or it might not be. It might be, but it might not be. Okay, so something that we know is the surface area. So our surface area, let's call it S, is equal to the bottom, so that would be x squared, plus, now there's no top, but there are 4 sides, and each side is going to be x by h. So 4 sides, and they are each area of xh. So our surface area is x squared plus 4xh, and they gave us a value. This is equal to 108 square inches. Okay, then what are we trying to do? We are trying to maximize our volume. So what we know is that volume is going to be equal to length times width times height. So in this case, volume is equal to x times x, which is x squared, times h. So here we're having a small issue because we have 2 variables, x and h. Good thing we also have 2 equations. So what we're going to do is actually go back up to our surface area equation and solve for h. So let's first, I'm going to ignore this s equals for now. Let's first subtract x squared over, so we have 4xh equals 108 minus x squared, and then if we divide both sides by 4x, we're left with h equals 108 minus x squared over 4x. And I'm going to cloud that because it's going to be important. Once we have that, we can actually go ahead and replace it in our volume equation. So we have volume equals x squared times 108 minus x squared over 4x. So I'm going to rewrite this so it's a little bit easier for me to visualize. Let's take this 4x out to the front. So we have volume equals x squared over 4x, just gives me x over 4 times 108 minus x squared. Running out of room here, let's come up to the top. So we can write this as volume equals 108 divided by 4 would be 27, and then we have an x, minus, distributing our x over 4 to the negative x squared, x cubed over 4. Now that we have our volume equation, we want to maximize it, so let's go ahead and take the derivative just like we have been. V prime equals 27 minus, bringing our 3 down, we get 3/4 x squared. We can go ahead and set this equal to 0, so we have 27 minus 3/4 x squared equals 0, so 27 equals 3/4 x squared. Let's multiply by 4/3 on both sides, so I know 27 divided by 3 gives me 9, times 4 is 36 equals x squared. Square rooting both sides, I get x equals plus or minus 6. Now this is a dimension of a box, so it's obviously not going to be the negative, so I have x equals 6. Now we want to find out what dimensions of our box. So our dimensions are x by h, so it would be 6, what are we measuring in here, inches by 6 inches by, we have to actually go back and plug into our h equation to find what h would be equal to. So h is equal to 108 minus 6 squared over 4 times 6. So we have 108 minus 36 is 72 over 4 times 6 is 24. 72 over 24 is just 3. So our dimensions would be 6 inches by 6 inches by 3 inches. And then final question, what is the maximum volume? So our volume, our maximum volume would be length times width times height, 6 times 6 times 6 times 3 would be 108 inches cubed. Okay, let's move on to a problem that is a little bit different. This one says a rancher has 200 total feet of fencing with which to enclose 2 adjacent rectangular corrals. Okay, I need a picture. We have fencing and we want 2 adjacent rectangles. So let's put a rectangle here. And adjacent would mean right next to it, one more rectangle, and they share that wall. Okay, and we want to know the dimensions of each corral. So let's go ahead and label this as x, x, y, 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 x, and x. So labeling each piece. And we want to maximize our area. Oh, and we have 200 total feet of fencing. Okay, lots of important information. So 200 total feet of fencing, that's going to be the amount on the outside. So that's going to be our perimeter. So I know that 4 times x plus 3 times y has to equal 200 feet of fencing. And then what I actually want to do is maximize the area of each corral. So just the area of like this one. So the area of that one is just x times y, my length times my width. Just like in the last problem, we're coming to an issue because we have 2 variables, but not a big stress because we have 2 equations, and we can go ahead and actually solve one for one of our variables. So let's go ahead and actually solve for y. So we have 3y equals 200 minus 4x. So y equals 200 minus 4x over 3. And now we can actually go ahead and plug that into our area equation. So area equals x times 200 minus 4x over 3. So let's go ahead and just distribute that x. And I'm actually going to break the fraction apart here. So we have area equals 200 over 3x minus 4/3 x squared. That's the equation that we want to maximize. So we can go ahead and take our derivative. So a prime equals 200 over 3 minus, bringing our 2 in the front, we get 8/3 x to the first power. We can go ahead and set this equal to 0. So we have 200 thirds equals 8 thirds x. Multiplying by 3/8 on both sides, we get x equals 200 over 8. 200 divided by 8, x just gives us 25. Again, we want to find our dimensions, so our dimensions are going to need an x and a y. So we can go ahead and plug back in y equals 200 minus 4 times 25 all over 3, which gives us 100 over 3, which is, yuck, 33.3. So our dimensions for maximum area would be 25 feet by 33.3 feet. Okay, here we go. Very last problem of the day. Number 4 says the area of a rectangle is 64 square feet. What dimensions of the rectangle would give the smallest perimeter? So again, we're going to be talking about area and we're going to be talking about perimeter. Let's get a quick sketch going. We have a rectangle. We don't know much about it, so let's go ahead and call it length and width. You can call it x and y or any two variables that you like. We know that the area, which is equal to length times width, is also equal to 64 square feet. It's a horrible 6. Let me try that again. And then we are looking to find the smallest perimeter, and we know our perimeter is all of the outsides, so it would be 2 times the length plus 2 times the width. Once again, two variables, no stress, we can solve. Let's get rid of this a for a second. Let's go ahead and solve for our length as equal to 64 over w. And now let's go ahead and plug that in. So our perimeter is equal to 2 times, replace the length, 64 over w plus 2w. Perimeter is equal to 2 times 64 gives us 128. We know we're going to be taking a derivative, so let's go ahead and bring that w up to the numerator and just give that a negative exponent plus 2w. Now that we have our perimeter equation, let's go ahead and take our derivative. So we have p prime equals, bringing that negative in front, negative 128 w to the negative 2 plus 2. When we set this equal to 0, I'm going to move that w back down to the denominator. So negative 128 over w squared plus 2 equals 0. Negative 128 over w squared equals negative 2. Let's multiply by negative 2, or let's divide by negative 2 and multiply by w squared. So switching this all around, we get w squared equals negative 128 over negative 2. So w squared is equal to negative 128 divided by negative 2 gives us a positive 64. So w is equal to a plus or minus 8. These are dimensions, remember, so we're going to get rid of the negative, and w equals 8. We also want to find our length. So our length is equal to 64 over 8, which is also equal to 8. So the dimensions for our smallest perimeter would be 8 feet by 8 feet. Okay, really fantastic job with day 2 of optimization. Homework 40 is in the homework packet, and as always, if you have any more questions, you can go ahead and reach out to your teacher.